Hello everyone, I am Sanjeev and welcome to the first presentation for section 2 in convex and combinatorial optimization. So this presentation is based on the unconstrained minimization, and here we will discuss a theoretical background needed for understanding the line search methods and various other algorithms for unconstrained minimization of a convex function. So an absolute question here is that why do we need to understand this theory and not directly studying the code? So the answer is that to understand the convergence analysis of the line search methods, to understand the dependence of these algorithms on the condition number of the matrices, that is the sublevel sets, and to understand the stopping criterion, that how do we choose a stopping criterion to stop that algorithm, we need to understand this theory. We need to have some theoretical background to understand that why do we use certain stopping criterion, and most important, how do we ensure that the algorithm that we are choosing is going to converge faster than the other algorithms. That is, how can we ensure that the algorithm is better than the other algorithms as compared to the rate of convergence. And most important, how do you ensure that the algorithm will converge faster to the solution? That is how अरे यार क्या कर रहा है यार. And most important, how do we ensure that the algorithm converge faster to the solution, which ultimately depends on the condition number of the matrices. So therefore we need to understand the condition number, we need to do the convergence analysis, and we need to understand the stopping criteria for these algorithms, and for that we need this theoretical background. So let's begin with the main topic of this presentation, that is the unconstrained minimization. So in the first part of this presentation, I will discuss the stopping criterion for the algorithms. So here's a problem. We have a function f of x and we need to minimize this function, and we have no constraints. That is, the problem is unconstrained minimization, where f maps a vector in Rn to a real number. That is, f is a mapping from Rn to R. The variable x is a vector in Rn. So our overall problem is to minimize this function, which is a function that maps a vector in Rn to a real number R. We need to minimize this function without any constraint. The only constraint is an implicit constraint, that is x should belongs to the domain of the function. Say your function is negative of log of b minus a transpose x. So an implicit constraint is that b minus a transpose x should be greater than 0, it should be positive. Other than that, we don't have any constraint. So here we assume that the function is convex and it's twice differentiable. That is, del square fx by del square exists. That is, f is convex and is twice differentiable. And we denote the optimal solution, that is the optimal value of x, which minimizes function as x star, and the optimal value of the objective function as p star, where p star is infimum of fx over all x belonging to the domain of the function. So the convexity and twice differentiability assumption implies that for x to be an optimal solution of this minimization problem, its gradient should vanish. So the gradient of f at x star is 0. That means that a gradient should vanish. Since this function is convex, therefore it will have a unique minimizer, and if the gradient vanishes at certain x, it means that the x is the optimal solution. And in general, this kind of problem is solved through iterative algorithms, though we can also find an analytical solution to certain problems. Say if your problem is half of x transpose px plus q transpose x plus c, then we just differentiate the function with respect to x and equate it to 0, and it will give us an analytical solution. But in general, the problems are not so easy, and therefore we need iterative algorithms to solve such problems. So an iterative algorithms works in this way. we need to give an initial value to the algorithm, that is the initial starting point, which is noted as x0, and then the algorithm updates the value of x at each iteration, and the updated values are x1, x2 up to xk, and as k tends to infinity, f of xk approaches the optimal solution. There is a p star, the optimal value of this function, the optimal value of this minimization problem. So to stop this algorithm, we need to have certain stopping criterion, and the stopping criterion is generally if f of xk minus p star is less than or equal to epsilon, where epsilon is some small value which is greater than 0, then we stop this algorithm. But in general, we don't know the optimal value. There's a p star, we don't know p star. If you already know p star, then we don't need to minimize this function. So in general, we don't know p stars, and therefore we need to have certain condition to stop this algorithm, and we will analyze this in this presentation. So as I mentioned, we need to specify a starting point, and the starting point x0 should belong to the domain of the function, and the condition required for proper working of these algorithms is that the sublevel sets must be closed, where sublevel sets is noted as a set of all x belonging to the domain of the function, so that f of x should be less than or equal to f of x0. So in order to derive this stopping criterion, we will make further assumption on the objective function f of x, and we assume that f is strongly convex, which implies that the Hessian of the objective function is a positive definite matrix. That is, Hessian of f is greater than or equal to m times I, where m is a constant which is greater than 0 and I is the identity matrix, and this condition satisfies for all x belonging to the sublevel set, where sublevel set is defined as S, which is a set of all x belonging to the domain of the function, so that f of x is less than or equal to f of x0. So we assume that the strong convexity holds for each x belonging to the sublevel set, where m is some small positive constant. So the strong convexity implies that this equation holds, which states that f of y is equals to f of x plus del fx transpose y minus x plus half of y minus x transpose times del square f z times y minus x, where z belongs to the line segment connecting x and y, where x and y and z are vector in Rn. So strong convexity implies that this equation holds for all x comma y belonging to the sublevel set S, where sublevel set is again defined as S is a set of all x belonging to the domain of the function, so that f of x is less than or equal to f of x0. So now if we replace the del square fz with this, then we get this inequality which states that f of y should be greater than or equal to f of x plus del fx transpose times y minus x plus m over 2 times norm of y minus x, where x comma y belong to sublevel sets, and this inequality holds since z also belongs to sublevel set. Since this function f is convex, therefore its domain must be convex, and if the domain is convex, then for any 2 points x and y in the domain of the function, and if there is line segment connecting x and y, then if z is on that line segment, then z should belong to the domain of the function, since the domain is a convex set. So by strong convexity, we get this equation, and by replacing del square fz with this, we get this inequality, and if we put m equal to 0, then we get the basic convexity condition, which states that for any function f to be convex, f of y should be greater than or equal to f of x plus del fx transpose y minus x for all y comma x belonging to the domain of the function. So with this slide, we have covered the most basic theory needed to derive the stopping criterion for the algorithm. So as we have mentioned, the stopping criterion for this algorithm is that f of xk minus p star should be less than or equal to epsilon. It means that we need an epsilon suboptimal point, where xk is an epsilon suboptimal point if f of xk minus p star is less than or equal to epsilon. And now we'll obtain the suboptimality condition using the gradient of the objective function fx. So we have this inequality this inequality, f of y should be getting equal to f of x plus del fx transpose times y minus x plus m over 2 times norm of y minus x squared. So we have this inequality, and on analyzing the right hand side of this inequality, we can easily see that this function is a convex quadratic function of y. Since this is a convex function, it will have a unique minimizer. There is a unique value of y which minimizes this function. And since this is a convex quadratic function, therefore therefore there is an analytical solution for this function, that is analytical solution for y which minimizes this function. So differentiating this function with respect to y and equating it to 0 will give us the analytical solution for y which minimizes this function. So let's differentiate this function, and differentiation is quite easy. Just apply the basic rules for differentiation. The del over del y of fx is going to be 0. Del over del y of del fx transpose times y is going to give del fx, and del fx transpose times negative x. Differentiation with respect to y will give 0, and the differentiation of the last term, that is m over 2 times norm of y minus x squared, which is y minus x transpose times y minus x, it will just give us m times y minus x. So solving for the 0 will give us the analytical solution for y, which is given as y tilde is x minus 1 over m del fx. And now putting this y tilde in this inequality, since f of y is greater than or equal to this function, therefore f of y should be greater than or equal to minimum of this function. And therefore we get this inequality that f of y should be greater than or equal to y tilde, since y tilde minimizes the function on the right hand side. Therefore f of y is going to be greater than or equal to f of y tilde, which is equal to fx minus 1 over 2m norm of del of fx squared for all y belong to sublevel sets and all x also belong to sublevel set. And since this inequality holds for all y in the suboptimal set, therefore this inequality should also hold for the optimum solution, that is x star. So putting y equal to x star gives us this inequality. There is the optimal value of the objective function, there is a minimum value of the objective function, p star is going to be greater than or equal to f of x minus 1 over 2m times norm of del of fx squared. Which gives us that norm of del fx squared is greater than or equal to 2m times fx minus p star. So here we have obtained the stopping criterion as is apparent. So to stop this algorithm, we need the basic condition that f of x minus p star should be less than or equal to epsilon, and we have that norm of del of f of x squared is greater than or equal to 2m times fx minus p star. So if norm of del of fx is less than or equal to 2m times epsilon 2m epsilon to the power half, then it implies that f of x minus p star is less than equal to epsilon, which implies that x is an epsilon suboptimal point, which is the desired solution. Since we cannot achieve the exact minimum value, we put the stopping criterion in the algorithm, that if f of x minus p star is less than equal to epsilon, then the algorithm should stop. And since we don't know p star, therefore we seek for alternate solution to stop this algorithm, and the solution is in terms of the gradient of f. If the gradient of f is too small, that is if it is smaller than some pre-specified constraint, where constraint some small positive value, if the norm of the gradient is smaller than that value, then the algorithm will stop. And hence we have derived the stopping criterion for our algorithm, and the x returned by the solution is epsilon suboptimal point, since f of x minus p star is equal to epsilon. So in the second part of this presentation, we will analyze the condition number of the alpha sublevel set, and then we will move on to the condition number of the Hessian of the objective function. So as we have this inequality from the previous section, from the previous part of this presentation, that f of y is greater than or equal to f of x plus del fx transpose times y minus x plus m over 2 times norm of y minus x squared for all x comma y belong to the sublevel set. And since f of y is greater than equal to this function, it means the sublevel sets are bounded, and if sublevel sets are bounded, then there is going to be some upper bound on the Hessian of the objective function. Therefore, we obtain an upper bound on the Hessian of this function, of the objective function. We have certain m, where m is some positive constant, such that del square fx is less than equal to mi, which means that del square fx minus mi is going to be a negative definite matrix, where I is again the identity matrix and m is some positive constant, and del square fx is a positive definite matrix on the sublevel set S. For all x belonging to S, del square fx is a positive definite, and this implies that there is an upper bound on the value of the Hessian of the objective function. So putting this in this equation, the equation we had from the strong convexity, we have this equation: f of y is equals to f of x plus del of x transpose times y minus x plus half of y minus x transpose del square f z times y minus x. And since z belongs to S, therefore putting this in that equation, we get this inequality, that is f of y is equal to f of x plus del of x transpose times y minus x plus m over 2 times norm of y minus x squared for all x comma y belong to the sublevel set S. And using the same method as we have used in the first part of this presentation, that is, this function is again a convex quadratic function of y, and therefore differentiating this function and equating the result to 0 will give us a unique value of y which minimizes this function, and again putting that value of y in this function will give us another bound on the optimal value of this function, that is p star is equal to f of x minus 1 over 2m times norm of del fx squared. So this is our inequality, and we have this bound, this lower bound and upper bound on the Hessian of the objective function. There is del square fx is greater than equal to mi and is less than equal to capital M times I, where I is the identity matrix, and the upper bound on the condition number of this Hessian matrix is given by m over m, which is the ratio of the largest to smallest eigenvalue. I rephrase, this is not the condition number, there is an upper bound on the condition number of this Hessian matrix, and the condition number is the measure of anisotropy or eccentricity or odd shapes of the sublevel sets of the function near the optimal solution. So here we will see the condition number of the alpha sublevel sets. So an alpha sublevel set is given by C alpha, where C alpha is set of all x such that fx is less than or equal to alpha, where alpha is greater than p star and is less than or equal to f of x0, which is the initial value. So applying the previous inequalities at x equal to x star, that is, we have two inequalities. The first one is that f of y should be less than or equal to this function, and second one is that f of y should be greater than or equal to this function. So we have these two inequalities, and we'll analyze these inequalities for x equal to x star, and we will use that del of f of x star is equal to 0. So using both these inequalities and using del of f of x star is equals to 0, since the gradient of the function at optimum should vanish, and utilizing that f of x star is equals to p star. So we get these two inequalities, that is f of y is less than or equal to this value and is greater than or equal to this value. So now utilize the alpha sublevel sets, that is set of all x as f of x is less than or equal to alpha. We replace f of y with alpha, which gives us two inequalities. The first one is that norm of y minus x should be less than or equal to twice of alpha minus p star over m to the power half, and second one is that norm of y minus x is less than or equal to twice of p minus alpha minus p star over capital M to the power half. So it means that the alpha sublevel set is bounded by two balls of radii twice of alpha minus p star over m to the power half and twice of alpha minus p star over m to the power half. So this ball is an outer ball and this ball is an inner ball, and alpha sublevel set lies between these two balls, and these are the radii of these two balls, and the ratio of the squared of the radii of the outer ball to the inner ball gives the upper bound on the condition number of the alpha sublevel set. So the upper bound on the condition number of the alpha sublevel set is given as a ratio of the radii squared, which is m over m. So this was all about the condition number of the alpha sublevel sets, and now we will move on to part 3 of this presentation, which will analyze the condition number of the Hessian matrix, which plays major role in the Newton's method. So here we will do the Taylor series expansion of the objective function f of x around the optimal solution x star. So the Taylor series expansion of f of x near x star is given as f of y, which is approximately equal to p star plus half of y minus x star transpose times Hessian of the objective times y minus x star, where we have used that the gradient of f at x star vanishes. Therefore del of f of x star transpose y minus x is equals to 0, since gradient is 0. So if f of y is equal to alpha, where alpha is close to p star, then we get the alpha is approximately equal to p star plus this term, and subtracting p star from alpha and multiplying by 2 will give us that the sublevel set C alpha is approximately equal to set of y, such that y minus x star transpose Hessian of the objective function at x star times y minus x star is equal to twice of alpha minus p star. So as we can see, the function y, this inequality, that is y minus x star transpose del square fx star times y minus x star less than or equal to twice of alpha minus p star, defines an ellipsoid which is centered at x star, and therefore the sublevel set is an ellipsoid centered at the optimum value, that the optimum which is denoted by x star, and therefore the condition number of the sublevel set near the optimum value of the x is going to be the condition number of the Hessian of the objective function near the optimum solution, and this will play a major role in the Newton's algorithm, and we will analyze the condition number, the role of the condition number in the convergence of the algorithm in the steepest descent and the line search methods. So let me repeat this part once again. We have done the Taylor series expansion of fx near x star, and we have chosen the value of alpha such that y is equals to alpha, where alpha is close to p star, and using this we get that alpha is approximately equal to p star plus half of this term, which gives the sublevel set is an ellipsoid centered at x star, that is the center of the optimum value of x, and therefore the condition of the sublevel set is going to be the condition of the Hessian of the objective function near the optimum. So that's it for this presentation, and the next presentation in section 2 of CCO 1011 is going to be on exact and inexact line search methods and the MATLAB implementation of these algorithms along with the MATLAB code. And also the matter of this presentation, most of the matter of this presentation will be directly applied in the presentation second, and this presentation will also be referred in third and fourth presentation. So that's it. Thank you for watching this presentation. I'm Sanjeev from searchingeye.com.